if I'm going too fast, slow me down. But it is going to be difficult to capture everything that happens on the screen. The recording will help, particularly in this kind of lecture. But what you need to focus on is what I call the art of the possible. What is possible to do with Comsol? Get a general idea. Specific sequence of menus and buttons that you need to push, I cannot teach you all. You need to learn that on your own. Okay. So I'm kind of opening the door to the world of Comsol to get you started, to lay out the structure of how it is set up so that you know you can play on. By doing one assignment on that, you will get a little depth, and then, of course, we will have an entire course on computational transport phenomena, which is an optional elective course if you guys want to. That's, I think, probably next fall. And there we'll go into the details of how Comsol does the magic. How does it solve these Navier-Stokes equations? Okay, the first thing that we need to do is when you go into the lab next door, Comsol is installed on all the machines. There are 30 machines or so. It's installed. I think it's also installed in the graduate computer lab. So you just start, hit the start button and look for Comsol Multiphysics 4.2. Now you will find in your machine several options. In mine, I don't have those. I guess, where is it? Yeah, if you go to all programs, Comsol. See, I have multiphysics, and then I have a client server. Can you guys see in the back? Is that big enough? But you'll also have on this room Comsol multiphysics with MATLAB. That's what you would start, because you need to have communication between MATLAB and Comsol. But today I'm not going to do that. I'm just going to introduce you to Comsol. So I just click on that and start the Comsol. The Comsol works in different ways. One is it is actually running on my laptop. The other one is what they call a client server. So if you have a huge problem, then you can run it on a powerful server. Your terminal would be a client. Your laptop will be client. You'll be remotely connecting to it. Okay, so this is the first window that you will see when you start up Comsol. Okay, so here there are several folders. This is a graphics folder, and in this region you will interact graphically, creating your geometry, plotting, and things like that. And this is the model wizard, which allows you to build the model. What is the particular physical situation that you're going to simulate? Okay, and this is the model builder, where it actually assembles the specific choices that you make through the wizard. So the wizard allows you to pick or make certain choices, and that will be added to the model builder on the left side. Okay, and then here you have messages from Comsol about its progress. Now, what is Comsol? Comsol is a simulation software that essentially solves partial differential equations coming from a variety of engineering field, engineering and science. Okay. So it has fluid mechanics built into it, it has solid mechanics built into it, it has electromagnetics built into it, transport phenomena, heat and mass transfer, they're all pre-built modules that are available. So it's essentially a PDE toolbox, a PDE solver. It actually evolved as a PDE toolbox from MATLAB, but into a full-fledged program by itself. So the first choice that you need to make is select the space dimension. Okay. So you want to decide whether your problem is a 3-dimensional problem, 2-dimensional problem, 1-dimensional problem, or 0-dimensional problem. So when you see things like that, you need to have an intuitive feel for what they might mean. What do you think this might mean? The dimensionality of the problem says in how many space dimensions the things can vary. If it is velocity or pressure or temperature or composition, how many spatial dimensions does it vary? Okay, so 0 dimension means there is no variation in any of the spatial dimension. So it could be a lumped, what you call a lumped model. Okay, 1 dimension means there is only one direction in which the temperature varies, for example. So if I have a long rod and I'm heating the rod at one end and I want to see what is the temperature profile, there will be some temperature variation in the cross section, but the rod is thin, so I can assume that the variation in the cross section is negligible. So I can treat that as a 1-dimensional problem. We have looked at 1-dimensional and 2-dimensional problems in fluid mechanics. So in our case, what I'm going to do is, let me just show you first the geometry that I'm going to build. And the problem that we are going to study using Comsol is the following. Okay. And perpendicular to the board, it's infinitely long. It's a channel. So the liquid is coming in and liquid is going out. And these are all walls. And I want to obtain the velocity field and the pressure field by solving the Navier-Stokes equation for this geometry. Now, I need to put a set of coordinates. So let me say this is x, that is y, and in the third direction I have z. Now, the problem that you are going to study in your assignment is this geometry. It's basically a converging channel, but it's converging in such a way that this is given by an equation. 1 plus, I don't remember right now, 1 over, I think 1 plus x over L or something like this. Okay, so that equation is given that generates this curve. That's why you need MATLAB to generate that curve and feed that information into Comsol. Okay, but the problem I'm going to do is a simpler one. I always get you to do the more difficult one. Right? The simpler one is just straight lines. Okay, so let's just get started with a simpler one, and then if you need help, I will give you help on MATLAB interface with Comsol later on. So our job is to solve the Navier-Stokes equation in this two-dimensional plane. I'm making it two-dimensional because in the third dimension it is the same. It's infinitely long in the third dimension in the z direction. So if I cut a plane, xy plane, at any z value, I'll get the same velocity profile. So my velocity field, I need to make a proposal. What will that be? Vx as a function of x and y, Vy as a function of x and y, and Vz will be 0. So there are two velocity components and they both depend on x and y direction. So I can simplify the Navier-Stokes equation, but I cannot solve it analytically. There is no analytical solution for such a problem because the problem is already nonlinear. Okay? So the moment you go from 1D to 2D, you need to make a lot of approximations to get any analytical result. That's one of the things that you're going to do in your assignment, make approximations. But in here, we are going to try to get the exact solution numerically. Okay? So is the problem clear? You want to get a velocity field by solving the Navier-Stokes equation for this converging straight channel and diverging channel. What would you expect the velocity to be? Suppose I put the inlet velocity to be parabolic. The inlet condition is such that the velocity comes in with a parabolic profile. In order to achieve that, I must have a long section before, so that the flow becomes fully developed by the time it reaches this part. What would you expect the velocity profile to be here? Suppose I ask you to sketch it based on intuition. What would that be like?
Going upwards as well because the velocity is in y direction right now.
The velocity, is there a velocity in the entrance? I'm telling you that it's coming from the straight channel. So as it enters, there is no y velocity component. There's only x velocity component. But this channel is going to force the liquid to go in this direction. So if I have to plot the velocity vector in this region, it's going to be like this. Right? And by the time it enters, it will still be coming in like this. And then in here, it will all straighten out again, particularly if the length is large. But when it comes out, what would happen? It will spread out. How many of you would agree that it will spread out like this back? Or how many of you would say, no, this is going to shoot out like this as a jet? Both are possible.
Does it depend on the velocity?
Depends on not necessarily the velocity, but what is the mechanism that causes the jet to shoot out instead of changing directions? Whether it is you are right in the right track, whether inertia is dominating or not. If the inertia is high in relation to the viscous forces, the jet would want to go straight. But if the viscous forces are large, that means if the Reynolds number is large, I will see this red kind of a behavior just shooting out. Okay, and I might in fact see a kind of a recirculation, meaning there is a kind of a wake that forms here at high Reynolds number. But at low Reynolds number, I will have the thing expanding and going like this. Okay, that's what my intuition tells me, and I can build an experiment, see whether it is true, or I can go to Comsol and solve it these days. So easy to solve. Okay, so we are going to see whether. So in order to answer all these questions, I need to be able to solve this problem repeatedly for different Reynolds number. So I need to now identify what Reynolds number I'm going to use. So we will see all those things as we set up the problem. Any questions on the problem? Okay. So what do I select now? 2D planar. What is the difference between 2D planar and 2D axis symmetric? 2D axis symmetric would be a situation where I have a tube So in an assignment, if I ask you to do this, a converging, diverging, but it's a tube, it's a circular cross section, okay? Then there will be an axisymmetric condition. So you would select 2D axisymmetric, which basically means Comsol will solve for in cylindrical coordinates, okay? And similarly, you have 1D axisymmetric, but in 3D, it's a general, okay? There is no symmetry condition imposed. So I'm selecting 2D now. What you'll notice is there are two arrows here, and they allow you to do the next specification. So I've specified the space dimension, what next? So if I click the next, it will immediately say, okay, I'm looking at a 2D problem, two-dimensional problem, and what physics? Okay, because remember, it is called multi-physics. So it says add physics, okay? Laminar flow, AC, DC. If you click AC, DC, for example, you have Maxwell's equation, electrostatic equation, magnetic fields. If you go to acoustics, chemical species transport, reaction, so structural mechanics, and in general mathematics. Mathematics will give you any partial differential equation. Okay, we can specify that. But for our purposes in this course, we need mostly this laminar flow. Okay, so we select laminar flow and then go to the next option. So I've identified 2D, I've identified the physics as laminar flow. I select next, and the next one it asks is, okay, what kind of problem do you want to solve? Is it steady or unsteady? Stationary or time dependent? Stationary means it's a steady state. Okay, so I select this as a steady state for this case, and you notice that there is nothing, no more, it's disabled next, because I've made all the choices that it needs to know. So I can just go and say, wave the finish flag, and it takes all those choices and puts it on the leftmost folder. Okay, so here I have laminar flow, the folder has created for that, and the study, a stationary flow, and it has created a results folder also, where the results will be stored. But the problem is still not specified. I have made certain choices for dimensionality and for the physics, which is the Navier-Stokes equation. What do I need to do next? I need to build the geometry. I need to tell Comsol what is the geometry in which I want to solve this particular equation. Once I identify the geometry, then I need to specify what are the boundary conditions I need to specify. Okay, I've identified the equation, the domain. Okay, now I need to build the geometry in that two-dimensional domain, and then identify the boundary conditions. So how am I going to do that? The moment I select geometry, you will see that all the menus here are populated with things that are related to geometry creation. Okay? For example, if you move the cursor near, it says draw point, and the icon itself tells you that you can place a point. Once you select that, you can go and click anywhere you want, and it will select a point there. It will place a point. The next one is for what? What do you think it will be? Drawing a line, drawing a quadratic curve, drawing a cubic curve, drawing a rectangular area, circle, ellipse. So you get the idea, right? So it gives you certain primitive things with which we can construct. Now you can also import directly a CAD file, for example from AutoCAD or any other geometrical program that has three-dimensional geometry. it can import the file directly. So it's really powerful in that sense for doing engineering type of calculations with real geometry. But for our purposes, I'm going to select this line. And remember, I'm going to draw that converging diverging channel, and I'm going to put that, let me just shrink. These are the things where I just do it, and you need to kind of, if you look at the zoom in, zoom out, okay? So why am I zooming out? Because I want enough range in the x and y direction for me to draw the entire geometry, okay? So I'm going to draw only the right half plane, and maybe let me zoom in a little bit, and I select this line, and I go and place my first point at 0, 1. 0, 1. And then I click the left mouse, okay? That point is set, and as I drag, it will continue to draw the line, placing the next one. So here I'm going to place one at x equal to 1 and y maybe 0.6. I click there. Okay, so that point is placed. Now I want to go up to 4. Okay, so I can go there and shrink it now, and then go up to 4. I guess I cannot. Did you notice something that funny happens? I'm going to have trouble. It automatically locks into those grid points. Okay, as I move the cursor, it'll place the point at the intersection of these. So I need to have enough resolution to continue to keep in 1 and then go up to 4 and click. So that point is fixed. Now I need to shrink a little bit and then go up. This is going to be trouble because I cannot do exactly at 5, okay, because it's 4.4 or 5.2, something like that. Let me just click there and then come down to -1 and then click there, back here. Everywhere I was just clicking the left mouse, but when I want to complete it, come back to I click the right mouse button, and that completes the geometry. It's a terrible looking geometry. Right? It's supposed to be symmetric, but it's not. We will fix that, okay, because I want to show you how to fix these things too when you make a mistake. Right? So now here is a zoom extend. So if you press that, it takes that geometry and fits it inside the window. But it's a horrible geometry. Okay, so let's go to see how to fix this. When I was creating the geometry, it automatically adds a folder called Bezier polygon. Okay, so if I click on that, it's basically a polygon. Okay, and it says that this polygon consists of 7 elements, 7 segments that are linear. So when I select that, it automatically put the coordinates of that particular point, and that is, if you can see, x is at 0, y is at 1, which is fine. The second point is x is at 0, y is, I want it at 0.6, say. So I can just go there and change it. Okay, and then I can ask it to replot, and then go to the next one. And the next one is at 1 and 0.6. Let me now get you into thinking. So I need to fix the next point. What should I put here? 4. And what should this be? 0.6. They automatically filled this for me as I was clicking.
Right, but the 0.6 and the 1 and the 4, were those given in the problem statement? Or
I'm just making it. Your problem, I have a function that you need to use to generate. Here I'm just making it up. I'm just told you that I want that shape.
Okay.
But if I'm asking you to really do a problem, I should give you the dimensions of the
So
problem.
you just approximated the dimensions with you.
Yeah, I'm just making up this geometry. But that looks better. And then go to segment 3, and this is, what do I want this to be? X is 4, y is 0.6, that is fine. X is, I want 5, and y to be 1 again. Okay, so as soon as you enter it, it doesn't update it until you go and say build. Okay, so now I need to go. What I wanted was 1 unit on the left side, 1 unit on the right side, and in between 3 units, 1 to 4. That's what I wanted because I could not click on the right points as I was building it. I have this problem. So how do I fix this one now? 5 and -1, that's fine. Okay. And then I select the next element, and this is 5 minus 1 and 4.6. Okay. And then I select the next one. I think you guys get the idea. I'm just killing time now. 4 and 0.6 and 1 and 0.6. That's fine. Okay, now I have nice symmetric geometry. Okay. So geometry is done, and then I need to go into the. What else would I need? Remember, I'm solving the Navier-Stokes equation, right? So I need to specify the fluid properties. What fluid is flowing through that geometry? Okay. So I go to the laminar flow, and here I have fluid properties. Okay. So this is domain 1. Now, the moment I select domain 1, it highlights it with the green. Now, you can have multiple domains in different physics, so it's really a very powerful tool. Okay, so when you have more than one domain, you will have different numbers appearing here for each domain. So in this case, I'm saying there's only one domain, and if you want to look at what equation it is solving, you can open up this folder, and you can see what it is solving. You should be able to recognize. This is the first equation is the momentum equation. You should be able to understand what each one of those terms are. What is the term on the left side? That one. The inertial term. And this is the pressure. This is the viscous term. Okay, and this term is 0 because it's incompressible flow. Okay, and F is any body force, gravity or any other external force. And this is your continuity equation. Now they have allowed density to be inside that, but if density is constant, that will drop out automatically. Okay, so this is the equation you are solving. So there are two parameters that you need to identify, rho and mu, that appear in this equation. You have to give them values. Okay, I need to give them values in such a way I control the Reynolds number. I want to have solution for a specific Reynolds number. Now, from material, there is a database. You can pick air, water, argon, whatever, or I'm going to say user defined and then put in a value. Okay, notice that what are the units for this? Density is kilogram per meter cube. So by default, everything is in SI units. So when I selected 1 here, that's 1 meter. Okay, and then I go to the viscosity, and I also select user defined, but here I'm not going to put a number. I'm going to put a variable. I'm going to call it as mu, a symbol. So it's a placeholder. I can change the values for that when I'm solving for a whole range of Reynolds numbers. So the way I'm going to control my Reynolds number is, what is Reynolds number? dV rho over mu, right? So d is some length scale, in this case the gap between the two, and v is the inlet velocity, and rho is fixed, mu is one I'm going to change. Everything else is going to be fixed. I'm going to change mu to change different Reynolds number. Please, if there are any questions, ask me as we are going along. Okay, so I've defined what the properties are. Now I right click on that laminar flow, and you will see inlet as a folder. So I can create that inlet. Then I go again to laminar flow and create an outlet, because I need an inlet and an outlet for this geometry. Okay. Now if I select wall, for example, by default it created the wall object for me, and it numbered them all from 1 to 8. There are 8 segments there, 8 wall segments, and they are all treated as wall by default. So if there is wall everywhere, there cannot be any flow, right? So I need to go and change one of them as inlet. So I can just go there and click on this boundary. It highlights that with red, and that's, you can assign it any property. So I'm going to call that as my inlet. So I have assigned it to the inlet, so I add that one. So that line segment 1 is now an inlet boundary. Okay, then you have to say, what is the velocity? I can go in there, that is the inlet velocity. I can put a value of 1. That is 1 meter per second. Okay. Then I need to go to the outlet, And so whatever you learned in the course in terms of the physics, you should be able to interpret when you see a program like this. So this is the outflow boundary condition, outlet boundary condition. What is the typical outlet boundary condition? Pressure. So we are saying that at the outlet, the pressure is set to 0. So think of it as a gauge pressure. Okay, so it is coming out. And remember, in incompressible flow, what did we learn? The absolute pressure magnitude does not matter because it's all gradient of pressure that appears in the equation. So if you fix the pressure as 0 and you calculate the pressure here to be 2, that pressure gradient is 2 pascals per 2 pascals per meter. Okay, so it's relative. You can fix the pressure at the exit at an arbitrary value. So now you have specified the inlet boundary condition, velocity, outlet boundary condition, pressure. And if you click on the wall, I did some mistake. What did I do? Outlet, I didn't identify that as the outlet. Okay. Now if I go and look at the wall, it identifies the remaining all of them as walls by default. Okay. So the first one is overridden by me, the last one is overridden by me, the remaining are all walls. And the wall, of course, the boundary condition is, you can have a no slip, a sliding wall. There are many types of boundary conditions that are possible. Leaking wall, when would a leaking wall make sense? That's one of the options.
Porous.
If it is made of porous wall, okay, so that you have some leakage rate that you can specify. Okay, any questions?
Can I see the boundary conditions of the inlet?
Of the inlet? There.
Yeah. So we choose the velocity. Why don't we choose the boundary conditions as other? There are other options.
There are other options here. Pressure, normal stress, mass flow rate. You can specify all of them. These are all options. Okay. I have just chosen to specify the velocity because I want to manipulate the Reynolds number. Okay. But for example, it's a good question because if I specify a pressure, immediately it says pressure is 0. If I specify 0 pressure at the inlet, 0 pressure at the outlet, what do you think it will give me as a solution? 0 everywhere, right? There is no flow. Now, if I want to generate a flow, I can make this as 200 pascals. Okay, then I am setting up a pressure gradient, so that will drive the flow, but I don't know what the velocity is. I need to calculate the velocity after I solve for the problem. Because there is a unique relationship between pressure drop and flow rate. If you give me the pressure drop, I can know the flow rate, or if you give me the flow rate, I can know the pressure drop. Okay, so the first way I set it up as a velocity boundary, and I specify the velocity as 1. That means I cannot specify what the pressure is at this boundary. It will calculate and tell me what the inlet pressure is. It will calculate and tell me what the inlet pressure is so that I have a velocity of 1 meter per second ending up with a pressure of 0 at the outlet. Understand? Yeah.
Since it's normal inflow velocity, does that mean it's a constant?
That's a good observation. I was hoping somebody will ask because what did I say in the problem statement? I wanted a parabolic profile, right? So if I want to put a parabolic profile, can I do that? Is that your question? Right? Yeah. So all you have to do is put an expression here in MATLAB expression, 1 minus y squared. Okay. So that automatically takes this as the y direction, and now you can understand why I set up the boundary from -1 to +1. Why did I do that? This is the perfect parabolic profile, only from -1 to +1. Okay. If I have -half to +half, then I need to figure out what is the profile that will still have 0 velocity at the boundaries. This one will have a 0 velocity at the boundary because y equal to -1 at 0, y equal to +1 at 0. But y equal to 0 in the middle of the channel, it will be 1 meter per second, the maximum velocity. That's what you're asking, right? So you can put in complicated expressions like that in any form that you are filling in. For example, viscosity. I want to put an expression for viscosity there as a function of temperature or concentration or gradient of the velocities. You can throw in an expression there. Okay, so wherever it accepts numbers, it also accepts an expression or even a MATLAB function, M file. Then it will go to that M file and calculate that property. Okay, good. So that got cleared up. Any other questions? Velocity field. See, some of the things even I don't know. I haven't clicked on them. So what you need to do is to be able to click that when you have that question pops in your mind. And okay, now let's think. What is it? What is it? What do you think it is? A velocity field means it has two components. You can specify if you expect the inlet coming flow to be having both an x component and a y component velocity, meaning that the velocity vector is not straight but it's at an angle. Then you will specify both vx and vy component here as a function of y, if you so choose to. Okay. So be bold, ask questions, click everywhere, and learn. Okay. There is another feature called dynamic help. I should I should actually show you how to take help by yourself. So if you go and click that, I don't want to do it now because it will open up another window and existing windows will all be shrunk. Okay, then you won't be able to see anything. But it gives you help dynamically in the context in which, well, let's open it up and maybe we can close it. Okay, so here you have a help window in the last section. Okay, now as you are clicking on each one of them, it will give you most appropriate help for that particular item that you are working on. Okay, so that's the idea for dynamic help. I just need to see how I can close it. There. Okay. Any other questions? All right. So we have set up the inlet, we have set up the outlet. This is something that I need to kind of ask you to accept faith in if you haven't done a numerical methods course. Yeah.
The boundary condition on the wall might have been changed.
Did I change that?
I don't know.
Yes, thank you. Thank you. All right. And outlet is pressure, inlet is velocity, that's fine. Initial values, what does that mean? There is a folder for initial values. To understand these, you should have taken a course in numerical methods for solving partial differential equations. Because when you're solving partial differential equations, computers cannot solve differential equations, so they convert that into a set of algebraic equations by discretizing. So the process of discretization is called, is a process using finite element, finite difference, finite volume. There are many methods. These are the things we will do in a computational transport phenomena course. And that's what we need to do now. We need to discretize the domain into fine meshes. And the error, the numerical error that you encounter depends on the size of these meshes. The smaller the mesh size, the more accurate the result is. So in each one of these mesh points, you need to give an initial guess on what the velocity is, what the pressure is. It will start with that and it will use an iterative method to converge by solving the Navier-Stokes equation. So this initial value simply means what is the initial value for u, v, and p. Remember, these are the velocities that we are solving for. Three unknowns. Two-dimensional problem. There are three equations, x momentum, y momentum, and continuity, and the three velocities, u and v and p. So we are saying initial guess, take everything to be 0. Okay, that's the initial guess. Now, when you go to the mesh, it says physics control mesh, normal. Let's just say normal and say generate, build. So it builds a mesh for you. Okay, so this is basically a triangular mesh, so it divides the entire domain into small triangles. You can zoom in and see sections of it if you want. Okay, in fact it uses quadrilaterals, rectangles near the boundary and triangles. It puts more points near the boundary than in the middle. Why do you think that is useful? The boundary has the sharpest gradient. The velocity gradient is the largest near the boundary. So because we are approximating the differential equations by algebraic equations, derivatives by its approximations, the derivatives have to be evaluated accurately. So you need mesh points that are close to each other. And this is why when you select physics controlled, when it knows a boundary is there, a wall is there, it put more points near the wall. Okay, and you can play with this. User control, then you can specify what size you want the mesh to be. Okay, so I think we will just work with here. You can specify what is the size, coarse, fine, etc., normal, and free triangle. So here I don't have closer grid points near the wall. It's kind of uniform everywhere. When I select, I mess it up. So let the program make those choices for you. Okay, so physics controlled, and mesh it one more time. All right, so now I'm ready to solve the problem. So I go to the next step. So you basically have to go down, filling out everything on this side. Now, on study, and every one of them, in fact, if you right click, it will give you more options. For example, the way that I added the wall, the inlet, etc., is by placing it on laminar and then right clicking it. It gives me a set of menus. So in the same way, when I go to study and right click, the first option is compute, solve for the problem. I'm going to hit this button and I'm going to get an error message. I want to see whether you can diagnose what the error message is. I feel that I have kind of set up everything, and here it says there is an error, failed to evaluate expression. What do you think it could be?
There is no initial value for velocity. You said 1 minus y square.
That's a good guess, but that's legitimate because y is defined at every point in here. So it will take points between -1 and +1 and calculate those velocities. So the problem is not there, but something related to that. There is one place where I put for properties viscosity as mu, and I didn't define mu wherever. So when it goes to calculate that term in the Navier-Stokes equation, it needs a value for mu. So if I had put in a value of 1, it would have worked. Okay, now I can go and say compute again, and it'll compute. And when it computes, it'll give you this. It really went very fast. Okay, so it gives you the convergence plot here, which tells you how does the error decrease. Okay, the error is 10 to the -5 right now. Okay, error in the algebraic equations is 10 to the -5. So it's a converged result, and then immediately it populates it with the solution. So immediately you see a contour plot of the velocity magnitude. Okay, so now you can start interrogating and getting answers to specific questions that you have. For example, here on the results, here is the velocity field. If you go to the pressure field, that's the pressure field. These are contours, constant values of the pressure. So what can you say about the pressure in the rectangular region in the middle? There is no pressure variation in the vertical direction. Okay, so the pressure gradient is only in the x direction. There is no pressure gradient in the y direction. So there is also no velocity in the y direction. But in this region, what happens? There will be a velocity in the y direction because the converging channel. Okay, and so there will be a pressure gradient. Now you can plot the pressure gradient also. Again, if you click this on the right, you will get a lot of options, and one of them is contour, which is what it is showing. Now let me just do a surface on that. Did it do that? Okay, the other thing that you need, here I am on the pressure folder, okay, and I have selected a pressure surface contour, but it still has in it the velocity, so I can plot any variable. Okay, so if I click here, it says laminar flow, and I can plot all of these quantities variation in space. Okay, why would viscosity change in space? Certainly not for this problem, but if I have a non-Newtonian fluid, viscosity will change as a function of strain stress. Then I may need to plot that. But let me just plot the pressure here and click this to plot. So that is the pressure profile as a shaded contour plot. Okay, so you can see that the pressure gradient is fairly uniform here, and there are pressure variations in the y direction. Any questions in terms of physics? Let's go to velocity, right click there, and one of the things that you will see is arrow surface. What do you think that would be? If you cannot guess, arrows. If you cannot guess, just select that and see what it does. Okay, plot it. There you see some arrows there, right? It's superimposing one on the other. So if you want to get rid of that, you need to go there, right click, and you can delete that. If you want to see only the arrows. And if you want to look at more arrows, here it plots 15 points in each direction. You can say plot 45 if you want. It gives you more dense plots. You can zoom in, as we saw before. So you can see that the arrows are pointed almost parallel to the wall. And of course the arrow should go to 0. The length of the arrow is proportional to the magnitude of the velocity. Okay? So you get an idea of how to look at the results from there. Okay? The results are all stored in this folder. Any questions? How would you interpret these arrows? The arrows, if you zoom in, for example, the length is proportional to the magnitude, and the direction shows you the direction of the velocity vector at that point. So you can decompose that. For example, if you take this, you can find out what is the x component and what is the y component of that. You can plot individual components in contour value also. Okay. For example, if I go to this and then put the surface there back. Okay, in the surface, I want to look at only the x component. So I go to velocity field and say plot the x component velocity. Okay, so this is a contour of only the x component velocity. Why is this looking the same as? Let me ask you some questions. Okay, remember this figure. This is the contour plot of x component velocity. Now I'm going to change that to this one, SPFU. What does that mean? That's the total magnitude of the velocity. That is square root of ux squared plus uy squared. That's what it's going to plot now. Do you see any difference? Why is it not different? Because uy is very, very small. These channels are not sharp enough to create a very large Vy component. So you can look at the magnitude. The magnitude of the velocity is something like 1.6. Now I want to look at the magnitude of the Vy component. Okay, so I go in there and plot only the y component. You can see where y component is large. Remember, green is 0. So in the middle of it, there is no y component velocity. Okay, and here it is negative, it's positive. There it's negative, it's positive. The y component. So you can get very quickly an overall picture of what the flow pattern is by selecting and plotting and trying to digest all the information. Now, one of the things that we said is we wanted to change Reynolds number and see how the velocity vector looks like, right? So let's do that. Let's go back to the magnitude. So what I want to do is I want to parameterize the problem. I want to solve this for various values of the parameters. So I'm going to go into the fluid properties and make this as a variable mu. Okay, but when I make this into a variable mu, I need to be able to specify the values for it. So I can go to the global definition here. So in your model, in many places you can have these parameters. You can define all those parameter values in one place, and that place is called the global definition. Okay, so here, definition, what's that? Parameters. Right click on that global definition. It gives you parameters, select parameters, so it gives you the parameter folder. You can come in there and define your variable. The same symbol that you defined there. So mu is this, and what is its value? 1. And you can put a comment here if you want to say what it is. Viscosity. Oops, where is it? Yeah. Okay. So I have defined the symbol mu. So when it solves a problem, it comes to this table, picks up the value. Okay, that's one thing. The other thing I want to do is in the study stationary, I right click that. Is it here? Parametric sweep. So I select the parametric sweep. That allows me to define which parameter I want to sweep and over what values. So here I can say add the parameter value. Because I have defined it in the table, it says there is only one parameter in your entire problem. The rest are all constants. Rho is a constant. All these geometrical numbers are constant. So mu is the parameter I want to change. So I add it to the parameter sweep. And then I say, okay, what are its values? So initially I've already said 1. So now I'm going to say solve for 1, comma 0.5, comma 0.1, comma 0.05, comma 0.01, comma 0.001. As I'm decreasing the viscosity, what happens to Reynolds number? Increases. So initially I started with a Reynolds number that's close to 1 because I picked my density 1, viscosity 1, dimensions are of order 1, velocity is 1, right? So my Reynolds number would be somewhere close to 1.5 or something like that. And then from that point I want to double it and then increase it progressively. So what would be the largest magnitude of the Reynolds number that I will be calculating? About 1000, of the order of 1000 or so, if I succeed in getting a solution for all those. Okay? So I have set that up. Now I can go to study and say compute. I'm not solving one problem, I'm solving a whole class of problems now. This is for the first value. Now immediately you can see the second, the third, the fourth parameters, the fifth parameter. All of them are converged. I didn't expect that, but it converged. But what do you see right away? The velocity. How does this velocity differ from the, what is the velocity for? What viscosity do you think it is for? Here you can see parameter value mu is 0.001. So it is for Reynolds number of about 1000 or so. Okay, and you can see that the jet just goes straight through. Okay, you can also look at how does it change for 1, for example. Now you see the difference, right? For 1, it was basically branching out. And you can look at any other intermediate value. And you can make a nice animation out of it. You can do a lot of things with that from that point on. But I think you get the idea, right? Any questions?
You can also change the velocity to make the viscosity constant.
You can. All you need to do is go to the inlet and put, for example, something like U max times this. So U max becomes your symbol. And then go to the global parameter definition and add here U max and put in the value that you want. Right? It's the same idea. So you can say center velocity. Right? And then you can do a parameter sweep on that. And you can keep mu as a constant, or you can keep both of them variables. Okay. Any other questions? I want to continue this. I wanted to show something, but it failed on me. Parametric sweep. Yeah. Comma 0.0001. Okay. And I'm going to say do this now. What am I trying to get at? Exactly. I'm trying to push it beyond the laminar flow regime to see whether it will still give me some results, meaningful results or not. It did. 10 to the minus 4. It shouldn't. It shouldn't, because the flow should become turbulent and numerically it should become unstable. When I was testing it in my office, it did give me a non-converged result when I had a viscosity of 0.001 already. But I think the grid may be too coarse in here. So there are a lot of numerical issues that one need to worry about when you're comparing it and interpreting the results physically. This may be, this is a result that is correct in terms of satisfying the Navier-Stokes equation. There is no doubt about it. It solves a two-dimensional Navier-Stokes equation, and this velocity field will satisfy that. But the real question is, if I go and do the experiment at that Reynolds number of 10,000, will I get this velocity profile in the lab? And the answer to that question is no, because the flow would have become unstable and would have become three-dimensional and time-dependent. Okay? So even though this is a valid solution, it's not a realizable solution because it's just computing an unstable solution to the Navier-Stokes equation. The other thing I said is that there is a backflow here, some sort of a convection, reverse flow in this direction at high Reynolds number, which doesn't occur at low Reynolds number. how do I plot that? Okay, this is the last thing I'm going to show, and then we will wrap up. So you can, this is a nice feature where you can get one-dimensional plots along any line in the two-dimensional domain that you want, plot of any quantity. The way to do that is select this, select the first point. Okay, so once you select that, it gives you a line. So you can leave that as the line and say, plot me the velocity variation along that line, for example. But I want to do this along the exit line. So I move the first point to there. And then I select the second point. And the second point is now the top in the middle. I want to put it down here. Okay. So I am drawing a line at the exit, and I want to plot the exit velocity to see what the exit velocity looks like. Okay. And here it immediately creates for me a 1D plot, one-dimensional plot. Okay. So I can select that. And here, for the 1D plot, by default, it has selected the magnitude. But I want to plot only the x component of the velocity as it goes out. Okay. And so let me plot that. Now interpret this graph. It's really a nice, powerful package. There's a lot of things for you with a few mouse clicks. What is?
That it is parabolic and it's going straight. It's not going towards the boundary.
You need to know there are several graphs. What are these graphs for? You need to know what they are for. So go to the legend, click the legend. Here it gives you the legend. So these are the viscosities. Okay, so it's basically each graph is a velocity variation of the x component for each Reynolds number. Okay, from 1 to a viscosity of 0.5, 0.1, etc. So what you notice here is the black one at the bottom, 10 to the minus 4, has a reverse flow. This is negative. In this region, and on the same thing on the other side, the flow is actually entering the channel, not exiting the channel. Okay, that's because of the reverse flow that you get. And of course, whereas in the low Reynolds number like 0.5 and 0.1, you don't have the reverse flow. You have almost a parabolic profile. Okay, but here in the center, the profile is not parabolic. It's almost like a flat jet, because by the time it comes out, the velocity is almost flat in the middle. Okay, so the velocity profile changes quite a bit as you change the Reynolds number, and it plots you for all the different viscosities. You can do this interrogation of pressure difference, for example. You can choose to, maybe I should go back to this graph. Is that the graph I have? I cannot see that particular line. Maybe. Okay, yeah, there it is. So across, for example, right through the middle, any quantity you can plot, velocity or pressure. But I would like to plot pressure to see how does the pressure change. Okay, so I've selected that. So let me go there and select pressure and plot. I made some silly goof here. Let me see whether you can figure that out. These are the pressure variations for various viscosities from 1.5, 0.1, etc. Okay, does that pressure profile make sense? What should be the pressure at the exit? 0. Where is the pressure 0 here? It looks like it's the inlet, right? It's not the inlet. What I did, the goof I did is, when I plotted that line, I selected the first point to be at the exit, the second point to be at the inlet, and what it plots is arc length, because it just takes the first point, measures the length along that line till the last point. So you could have a line plot plotted across this if you want. Draw a line from here, it will just measure the arc length along that, and whatever variable you are plotting, it will plot on that one. And that's why it looks reversed. So I need to really reverse it if I want to see it properly. But does it make sense? The blue one has a larger pressure gradient than the black one. black one is almost flat. Why is that? Of course, the viscosity is high. What do you expect? Larger pressure gradient, right? The pressure gradient is this. And you will see that the pressure gradient is not linear near the exit or near the entrance. But in the middle, it's almost linear. Pressure gradient is linear, but the dp dx slope is becoming smaller and smaller because dp dx is directly proportional to viscosity. So the smaller the viscosity, the smaller the viscosity, the smaller the pressure gradient. The larger the viscosity, the larger resistance, and hence larger the pressure gradient. So it's a nice physics tool for you to interpret and develop intuition, make sure that it agrees with what you do analytically, and that's what I want you to do in your current assignment. Solve the problem analytically and then approximately, because you cannot solve it exactly, and then go ahead and set it up in Comsol. And what I want you to produce, of course, is these graphs, okay, and then comment on those. I would like each one of you to work individually because this is very difficult for me to monitor. The thing that you're going to learn depends on how much time you spend in actually doing it by yourself. Any questions? Yeah.
I was just wondering about, like, suppose we didn't have an idea of, like, what Reynolds number would start giving us, like, a fair or something like that. And
Yeah.
we generate these results, and we suppose that they're accurate. Like, how might we troubleshoot this or get some kind of indication that this is an incorrect?
That's a very, very good question. This goes back to almost 25 years when I was a graduate student facing the same question. And I went to my supervisor and said, okay, I've written the code. It produced, pardon me?
Was Comsol then?
No, I wrote the program myself. You guys are lucky. You don't have to write it. I wrote the program myself. But that's for my master's thesis. Okay, so I was writing the program. And the same question, how do I know whether the results that I'm getting are right? Okay, so you need to benchmark that. You need to take a known result and compare it against it. So you need to, for example, for the geometry that you are doing, by setting the parameter, you can make it into a flat plate. Before you start trusting the results for the converging channel, do the one for flat plate, where you have the analytical result, and you compare, okay, and make sure that it agrees well. Then you know that your code is working in the limit, and then you can push it away from the limit into the domain where you want to really explore, and nothing is known. Okay, so it's a very important question to make sure that don't trust anything comes from these simulators, whether it is Aspen or whether it is Comsol. Just because they produce pretty pictures, it doesn't mean they're right. Okay, so the computational fluid dynamics, I always say, is another acronym is colorful fluid dynamics. We project these colorful pictures and then people start believing it. You need to be very critical in making sure that what you get is the correct result. Okay, any other question?
You first talked about, you said that the viscosity was small. What do you expect?
Okay, yeah. If I keep the viscosity small, what do I expect? Let me see whether I can reproduce that. I should be able to reproduce that. I go to mesh. I think I selected a normal mesh now because I wanted the results to come quickly. Because when I select a normal mesh, for example, in the messages, you'll find how many degrees of freedom. So what it has done is it has reduced that partial differential equation to about 4,000 algebraic equations. So it's inverting a 4,000 by 4,000 matrix, and it does it very fast. Okay, but what I was doing in my office was to go for fine. Then I have about 30,000 mesh, more accurate result. Okay, it's 9,000. I guess I probably had even more. 9,000 elements. So it will be, each element has 3 unknowns: velocity 1, velocity u, v, and pressure. Right? So it will already give you about 27,000 equations or so, like that. So if I do this, so it's now doing for, here is a log, for mu of 0.1, error 10 to the minus 7. You can watch here what happens to the solution. 0.05, See, 0.01, it's already beginning to have trouble. So if you watch, it's not able to converge to 10 to the minus 6. So what it is doing is, okay, I give up trying to get a solution for 0.001. Let me try for half the interval. Okay, so it takes half the step. That's why you get these 0.00325. It picked the value of the viscosity to try to reach. Okay, and this is what happens. Okay, fail to find a solution for all parameters. Okay, so that means it did not converge for the very small values, and the last value that it converged is only for 0.00001. No, 001 it did not converge. You can look at the errors. This is the error in the solution. So that must be 10 to the minus 6 for you to conclude that it is converged. So for 0.001 it did not converge. 00156 it did not converge. So the last one that was converged was probably this 0.00325, about 10 to the minus 5. Because it tells me what is the error estimate. So it, for every value of the parameter, when I'm doing a parameter sweep in this log, say for now on for this value of mu, and this is the iteration number, this is the error estimate. So I look at the error estimate. So in one iteration, it has come down to 10 to the minus 5, which is what the answer should be, about 10 to the minus 5. If it's not able to get below that, it'll abandon and it'll put up that error message. And if you look at all the previous ones, like here, 0.001, it did not could not reduce the error. So it abandoned that and then said, okay, I'm going to try for a slightly larger value of viscosity, which is 0.00325. Okay. And you should actually track the whole thing. Okay, you look at here, 0.5. That was one of the values I asked for it to solve. And it converged in one iteration, 10 to the minus 6. Done. Okay. Then it goes to the next value I have in the list, which is 0.1. 2 steps, 2 iterations, 10 to the minus 7 converged. It's done. Okay. Then it goes to the next one, 0.05. 2 iterations converged. 0.01, it did not converge. Okay. So I guess it deemed it as converged maybe because it's, yeah, it did, because it then picks the next value, 0.001. Okay. And for that one, it did not converge. So it goes back and tries other values and eventually gives up. So the key factor that you have to look at for convergence is this, but it will give you an error message if it did not converge. Okay. So there is really a lot. It's a very powerful program. What we have seen is basically scratch the surface. It can solve electromagnetics, it can solve solid mechanics, it can solve microfluidic devices and stuff like that. So there is an enormous power behind such simulation tools, but you need to use it with intelligence. You need to understand the physics, you need to understand the numerics before you can reliably use these things. Okay, any other questions?
What's the density and the viscosity in this problem?
In your problem, I said pick the numbers that way I know no two have copied. Right? That's my value of it.
Numbers about the viscosity and density.
Pardon me?
I didn't find the values.
I didn't give you. I didn't give you. I said pick your own values. That way I know no two will pick the same value, right? If you two pick the same value, I know you work together.
And just to compare the Comsol result and
That is the key. So you pick the same values of mu and rho in your analytical result when you plot it and in Comsol. So that you can plot one on top of the other and see how well they can do it.
how good the data of the Comsol and the plot?
Well, very good, very good. I really don't know how to do it, but you can do it. You can write out the data. You can take the data from here and write it out into an Excel file when you have a line data. And then you can plot it in Excel or MATLAB. But how, I don't know. Here, add plot data to export. Right? I guess, that's it. That's the spirit. Right? I open the door, you explore. Okay, so this should do it for you. So you select that and you say, okay, what is the data format, spreadsheet, and give the file name, the data goes there. What goes there, I don't know. You open it up and you see. It depends on what you selected, right? You select pressure, pressure data will go. You select the velocity, velocity data will go. It's really very easy, very intuitive. Okay. Can I exit? No more questions? Was it useful? It's a lot of information in one lecture, and I hope it got recorded. So put that up. Okay. Okay. We have only 15 minutes. All right. We'll just. I want to continue. What I want to do. The plan from now on in the rest of the course is to deal with more complicated flows and to deal with heat and mass transfer. So you see the similarity between fluid mechanics, heat transfer, and mass transfer. And Comsol has the ability to solve heat and mass transfer equations also. So maybe in the later on I will give you one assignment that explores that. So in the last lecture, if you remember, we solved the forced convective heat transfer in a pipe, cylindrical pipe. And it again in the laminar regime, a known velocity field. So the velocity is the one that governs the convective transport of energy. So that velocity field is given by the parabolic profile. So we are looking at the fully developed region, and whatever that is axially convected is radially conducted. That's the balance. So you take the energy equation subject to that assumption of the velocity field and temperature field, simplify it. How does Comsol do that? Comsol will solve all the terms in every equation. When you say 2D, of course it drops the third equation. But in those two equations, you will have derivatives with respect to z also, right? Those will be dropped because there is no variation in there. Okay, so Comsol doesn't make the simplifying assumptions that we make to get an analytical result, but those terms will naturally die out because there are no gradients in there. Computes a gradient, it becomes 0. Okay, so in this case, we simplified it specifically for one-dimensional problem. And the important concept that you need to understand here is this concept of a fully developed temperature profile, fully developed thermal region, where we have written down this integral condition, which simply says in words that if I'm putting a flux through the wall, a constant flux every unit length, the energy content in the liquid must go up by the same amount. So if I put in Q0 through the wall, the energy increase in the liquid is Q0 for every unit length. And so the wall temperature increases linearly, the bulk temperature increases linearly, and we solved for both of them. Okay, so this is the temperature profile that we obtained in dimensionless form, and this concept of a mixing cup temperature is also very important for you to understand. It is the temperature that you would measure if you collect the fluid in a beaker and mix it up. That's why it's called a mixing cup temperature. The temperature is a function of the radial position. So if I sample at one particular radial position, I will get a different temperature at each radial position. But if I collect them all together, I will get the mixing cup temperature that has to be calculated in such a way that the energy, what is this one? V times T. You multiply this by rho Cp, that's your energy content, divided by the mass flow rate. That gives you the temperature. And this is an important analytical result. That the Nusselt number in that limit is a constant, 48/11. Very similar result for friction factor times Re equals 16, a constant for a pipe flow. And now I want to set up the problem in the remaining 10 minutes for the next type of convective heat transfer, which is called the free convection or natural convection. Okay? So this is a problem that occurs in every window pane, double glassed window pane. Okay? Because what you have is two glasses and there is an air space in between. Why is the air space there? Because air is an insulator, a poor conductor of heat. So you can cut down the heat loss by putting this double pane. But what happens inside that pane is what we are going to look at. Okay? So one side is hot, the other side is cold. The outside is cold, the inside is hot, for example. So the fluid that is near this region is going to be heated up in here. When it gets heated up, it expands, its density goes down. and it is in a gravitational field. Okay, so this is going to rise. So that will drive. So the driving force for the velocity field is gravity and density gradient. Density gradient in a gravitational field gives rise to this buoyancy force, which you have seen before when you have two inhomogeneous material. A cork immersed in water is buoyant because of the density difference. But in here, it's the same fluid, but we are creating small density differences by heating it up. And so that creates an upward flow. In the same way, the fluid that is close to the cold wall becomes a lower temperature, higher density, it starts sinking. Okay? So we're going to assume, again for analytical result, we're going to assume it's an infinitely long plate. So what happens to the liquid? This just keeps on going all the way up, and this keeps on going all the way down. But in reality, what would happen? In reality, you would have a finite region like this. So in the middle, the velocity profile will be like this. But as it goes to the top, what should happen? It should just turn around, come down. So we would call these as the end effects. So we need a very thin plate and a very long plate so that we can confine our analysis to the middle region, developed region. And again, you have end effects on the other side. That's a problem you had in your midterm exam too, right? When you were pulling the rod, near the end you will have these kind of return flow. But in the middle, you can assume the flow to be one-dimensional. So what would be the nature of the velocity profile and temperature profile that I can suggest? For example, V is going to be, I need to put some coordinates here. What did you do? Okay, Y and Z. So perpendicular to the board, it's going to be infinitely long. So there is no flow in that direction. Okay. So what would I get? For Vx, it will be 0. Vy, 0. Vz as a function of y only. So once again, we get a one-dimensional flow. That's an assumption, that's an approximation. That will be true in the middle zone. Now, if you set this up in Comsol, you need to select a finite length. But if you select the slit to be very thin, you can achieve this one-dimensional flow and compare it with the analytical result that we are going to get. Okay? And similarly for temperature, what I'm going to take is a function of okay. X perpendicular to the board, there is no variation, it's infinitely long. In the Z direction also it's infinitely long, so there is no variation. But in real life, in this region, that will not be true. T will be a function of both Y and Z. V will be a function of both Y and Z. And both components of the velocity will be present. Okay, so that's a problem that we are going to solve. Okay, so the important thing to understand is that the driving mechanism comes from the buoyancy force. Any questions on the physical description? Yeah.
What about if it wasn't in gravity field? Like, I know that the probably the heat, it would start going this way, but then there would not be like a recirculation. It would be kind of like the cold would be traveling one way and the hot another way, right? If it wasn't in a gravity field.
Good question. I like questions that make you think. Okay. Imagine that this is in the space shuttle. There is no zero gravity. That's what you are asking. Okay. Is there any mechanism for velocities to develop? Of course, if you are heating one side and if you are cooling this side and if there is an air in between, there has to be conduction, right? What sets up the temperature gradient here, you will see very soon in the equation. As long as there is a temperature gradient, conduction will always be there. Conduction can take place through air too, through fluid as well. Air has a thermal conductivity, just that it's very small. So we call it an insulator. Okay, but so that temperature gradient will be set up in that environment also. And that means the liquid or the fluid in these regions will have different densities. But will they respond? They won't. Because there is no gravity, there is no driving force. Okay? So you will not see any convection, you will not see any fluid movement. So if you put a dye particle and want it to observe move, it will not move, it will just stay there. But if you put a thermocouple at different locations, you will see a linear temperature gradient.
Wouldn't the air like expand next to the heated plate in this case? But it still probably wouldn't move.
Okay. It will expand and it will contract in the other side. Okay. So the question that I think you are asking now is if the heating, if I put a lot of heat to it and the expansion is large, will that not create a flow? That's a good question. What should happen for that to happen? The heat that I put in should be so much that if the volume is constant, if I increase the temperature, what should happen according to the ideal gas law? If I keep this constant, I keep increasing the temperature, I should increase the pressure. So if I'm uniformly increasing the temperature everywhere, the pressure will increase uniformly. So there will be no flow. But the expansion that is causing this pressure increase, for example, because it's trying to expand, but it cannot because it's in a constant volume situation, right? So if I heat only this part, pump heat from both sides, no gravity, then I will see some sort of a flow. Why? Because the gas here expands and it has a lower pressure in the other region that it can move, right? So you need to kind of refine your question to pin down what it is. Good questions. Good.
In this situation, it is steady state.
Yeah, the analysis we are going to do is steady state. But one can do an unsteady state analysis, which will be more complicated, but not in Comsol. Comsol, everything is the same difficulty. Okay, I think we are almost out of time. Any?
Saying that it'll appear to have flow if there's a concentrated heat source.
If there is a concentrated heat source from both sides, the specific question that you was asking, and there is no gravity, then what happens is as you increase the temperature, the volume is constant, so the pressure will go up. So in that region, this region will experience, as it expands, it will experience a higher pressure. And so if the other region in this part is not heated up, it will push the gas away until it equilibrates. So it's not going to be a continuous pumping, but until heat is convected away in that other direction. Any other questions? Okay, so Thursday we have no class. Work on the assignments. If you have any questions, I'll be here Thursday, Friday. You can drop by. And if you need the MATLAB help, I'll see what I can do. Okay. Yeah.
What did you mean when you kept referring to the solutions as converging? This can converge to 10 to the minus 6.
Converge meaning that I guess I closed it. The error in the solution goes down to 0. Okay. So what do I mean by the error? Suppose you have 3 algebraic equations in 3 variables x, y, z. Okay. And one of the ways of solving is a direct method by Gaussian elimination. Okay. The other one is by iterative method where we say, I'm going to put a guess for x, y, z, 1, 1, 1. And then I'm going to take the difference between the left side and right side and see whether it is 0. So if I put some arbitrary number like 1, 1, 1, it's not going to be 0. That's my error. Then I'm going to devise a mechanism whereby I get a better guess for x, y, z. And that's what Comsol does.
Okay.
So as it drives to those better guesses, the residual should go to 0. So 10 to the minus 6 is close enough to 0.
Right.
That's what.